just looked at the clock. Okay, thermodynamics, our last lecture on the topic.
Yeah.
First, very brief review for the test. The test is going to be having a question on Maxwell-Boltzmann distribution.
Right.
And so you are either going to find, well, you're going to find one of these things. So we did all of those things in class already. None of them are new, but you just need to know how to get started and how to go through. And you need to know what the Maxwell-Boltzmann distribution means. So there's no point in repeating what I have already completely done, because you're going to go watch it on YouTube, you know. But it's going to be one of those things. Hello, you're not Randy.
I'm not.
Hello, Oksana. I was ready to mark Randy is here.
True. I'm looking for Dr. Seth.
He should be around.
What do you all learn?
Stop.
So, moving to stuff that would be covered on the final, because we can't cover it on the test today when we talk about today. So we're going to go through thermodynamics with the calculus base. So we have here our first law of thermodynamics. Change in internal energy is equal to heat added minus work done by the system. But here's where things get already confusing and interesting, depending on your point of view. Delta U. Remember, first law, energy can't be created or destroyed. And so basically we say the change in entropy, if we do this in calculus, or change in entropy, change in internal energy, how do we put change in calculus? And then we have Q. What would you put for the change in heat?
DQ.
No. No, we don't. Because what is Q?
Q is the transfer of heat.
Yeah, it's a change.
It's a change. Oh,
Q
it's
is already a change. And so that's why we had a delta here, but no deltas here or here.
So work has already changed as well?
Yeah, it's a transfer of energy.
Good.
So what we do is we put these, I looked it up this morning so I'd have the right word. Now I don't remember. I always say inexact, but it's not inexact. This is the way I was taught to do it. A D with a slash through it.
That's a partial?
No, it's not a partial. It means exactly the same as Q. But now we'll write it as a calculus form.
Okay.
So, right, like I said, it gets confusing here. And then when I was looking things up, I saw on Wikipedia that the entry there says that they use this version of delta. Remember, a partial is this delta.
Yeah.
That's a variant of delta. They're both delta. This is delta, that's delta, and the partial is delta. So the direction you draw that tail really makes a difference.
That's mind-boggling, but okay.
This here is using an old equation editor for Microsoft Word that almost put the D with the bar on it. I couldn't figure out how to do it with the new version, so I did this. Right, because that is a correct form.
Right.
Okay, so finish out the equation then. That's the calculus form of the first law. The change in internal energy is equal to the heat minus the work. Same words, but looking different symbols.
Right.
Now we have our definitions here of variables. Internal energy is U, Q is the heat added to the system, W is the work done by the system, and S, of course, entropy. Now entropy is not going to be on the test today because we didn't really give it anything except for the statistical explanation. But entropy has two equations that we call defined equations. One is ds is equal to dq over t. Now, if you take like general chemistry, they're going to tell you the change in entropy is equal to q over t. And of course, now from you understand, you see, well, let's call it incorrect. How's that? No, but that dq is q. But if you look at it in this form, you realize if temperature is not constant, that equation isn't correct.
If the temperature isn't constant,
Yeah.
it's not correct.
Right. You're going to have to integrate. The equation in the green box is correct. The one outside is not correct unless temperature is constant. And you can't even take the average temperature because it depends on how the temperature changes as you remove heat. If you have Q is equal to MC delta T, well, then it's pretty simple. But, you see, so there's a little extra work involved there. We're not going to focus on that. What we're going to do.
So what's the difference between the one delta Q and the other delta Q? Or the one DQ and the other DQ?
Okay, a D with a line through it and the funny D, they're the same. I was taught the D with a line through it.
Okay.
And I saw on Wikipedia today that the D with the
Swirling
alternates, is meaning the same thing.
Okay.
Okay, so what we're going to do is we're going to find equations for work and heat for ideal gases. So we're only dealing with ideal gases. That kind of limits us. We can use the ideal gas law. It makes our life a little easier. We have this stuff here. It's redundant. We've already gone through all of this to tell us that the work, thermodynamic work, is integral of P dV. Integral of P dV. Or in other words,
there. Okay, I see that again. Gotcha.
dW is equal to P dV, and then you integrate both sides, and you get this. If P is constant, you get that. Okay, so that's going to be key to our following work. So we start with the isochoric process. Why isochoric? Because it's the easiest. You want to start with the easiest.
Volume doesn't change.
So volume doesn't change. That was my question. So if volume doesn't change,
That means dV is 0, isn't it?
yep. So the work is 0. Isochoric, that's why we started with that one. Work is 0.
I like it.
Now, if work is 0, then we know from the first law that, right?
So
Since dV is 0.
So that means it's a perfect system, doesn't it? Or
Not perfect. I mean, there's no perfect anything. It's just a simpler transition.
wait, U stands for what again?
U is internal energy.
Oh, okay. So that basically means because no work's being done, all the heat that's put in the system
Makes it hotter. Yeah.
Gotcha.
Okay, so we add to that a definition. If you have constant volume, we say Q, the heat you put in, is the number of moles times the constant volume molar specific heat multiplied by the change in temperature.
Right.
Or in calculus terms, then, the D with this improper, that's the word, improper is what I always use. dQ is equal to NCV dt, right? Delta became D.
Yep.
But given this relationship right here, and that for an ideal gas, for any ideal gas, U is equal to the number of degrees of freedom, which is F is the number of degrees of freedom per molecule. And then I'll put times the number of moles divided by 2 R T, or using the ideal gas law. This equation, the equipartition theorem, applies to any ideal gas. Doesn't have to be monatomic. F is the number of degrees of freedom per molecule, so if it's monatomic, F is 3. If it's diatomic at low temperature, F is 3. At intermediate temperatures, F is 5. And high temperatures, F is 7. Remember we talked about that because you don't have enough energy to make them rotate or vibrate at low temperature.
Right.
Intermediate temperature, I believe they could rotate but not vibrate. Once again, I never get those straight. High temperature, they can do both.
Okay.
So that's why we just put F here, where F is the number of degrees of freedom. So if that's the case, then du must be equal to F over 2 N R dt. Or, since this is constant volume, I could also say it's equal to F over 2 VdP. Constant volume, do the product rule. V is a constant. You don't need to. Remember, we're doing isochoric.
Which means volume is constant, which means pressure is the one changing. Okay.
There's the product rule. But this one here is going to be 0 if it's isochoric. So why is that important? Well, since du, and I have it written over here, du is equal to, I'm going to change color just because I can. Du is this, but du is equal to dq, and dq we define as this. Then we have the relationship that says NCV, well, I see I forgot to change this to a D. Copy, paste, and forgot to change. NCV delta T or dt equals N F over 2R dt. So you can read from this. What is the value for CV?
F over 2R.
Which is why I have in parentheses, obviously. Yes. So for any ideal gas, CV, which is the constant volume, molar specific heat, is F over 2R. Now this is theoretical. We saw in class there's a little variation, but it's pretty darn close.
And R is radius, right?
No. R is the universal gas constant. 8.331 something joules per mole Kelvin.
So why, when we were talking at the beginning of the semester, we would use lowercase r for radius, and then we would use uppercase R for radius on a moment of inertia, and now we have an uppercase R for this gas constant. What's the deal?
We don't care?
Huh?
We for radius, sometimes we use uppercase, sometimes it depends on what move we're in. Whereas the gas constant, capital R, is always capital R.
I mean, I get that, but just the lowercase r and the uppercase R for radius.
I hear you. And it would
That's
be,
why I asked that stupid question on the lab exam.
it would be good if we at least use the same case always.
Mm-hmm.
You know, we're still going to end up having capital R means this here, like Q.
Right.
Q right now is heat.
Oh,
But Q is flow rate last test.
Exactly.
Next test Q is going to be charge. We're going to reuse, because we only have 26 letters, take out case and lowercase, that gives you, 52. Then we start adding in Greek letters. God help us, we could use Cyrillic, but we don't because we're not that adept.
I don't even know what Cyrillic is, so.
The alphabet they use for the Russian language or Ukrainian or...
Hard pass.
Or we could go to Chinese. We'd have it covered if we use Chinese.
We would, but harder or pass.
Yes, I'm with you there. Okay, so what do we have here? We have the equation that tells us what the CV is. But you know what we did? Oh, yeah. And Q is just going to be this thing here. And CV dt, where we know what C is. So we know what Q is. And what's the work?
Work is Q.
Look at the red.
Work is 0.
0, right. So for the isochoric, the outcomes for the isochoric are work equals 0 and Q is equal to change in internal energy is equal to the integral of N CV dt, where CV is equal to F over 2 R. So those are the important outcomes that we've come up with. We have equation for change in internal energy, for heat. I forgot to put the and for work. Yeah.
Okay.
So that's isochoric. And you can see, I know I wrote and said a lot, but it was simple. Is that Randy? That's Randy. Welcome.
Talk about the ride, yeah.
Yeah, we already reviewed for the test. We got that covered. Yeah.
It was pretty small, I'm guessing.
Yeah, it was pretty small, yeah.
The Maxwell Boltzmann stuff.
It's going to be one of the things that we did in class, last class period, which was 2 weeks ago.
Okay.
Yeah, you're gonna have to. I will give you that sheet. You'll have to use it, unless I say find the most probable. If I say find the most probable, what do you do?
Circle an answer.
No, this one's not multiple choice actually, because it says derive this equation.
Oh man.
For Randy's sake, I'll come back to this. Find the sum of the probabilities. That means you're doing integral of the Maxwell-Boltzmann distribution over all speeds from 0 to infinity. If you find the most likely speed, the most likely speed is the mode, right? And you do that by finding df dv, v most likely, equals 0, right? Because you're just finding the maximum for the curve. So that's the one that doesn't involve an integral.
That's the one that doesn't.
Right, because you're finding the maximum of the curve. Where's the curve maximum?
Right.
And then find the average speed. That would be, the average speed is integral from 0 to infinity, the probability of each speed times v dv. Right, speed times the weighting factor, add them all up, and that gives you the average
That's all
speed.
different from what's on the sheet here.
On that sheet, you just have integrals.
Yeah.
You don't have what they mean. Yeah, see, this doesn't have what they mean. This is how you do the math.
Good Lord.
So you're going to have to know this and then be able to use this to find the answers.
Right.
And then finally, find the RMS speed. How do you find the RMS speed?
Isn't that v squared dv?
And then square rooting it. Square root, integral from 0 to infinity, f of v comma t, v squared dv. Right, because RMS, first you square it. So that's v squared. Then you find the average. That's the integral. Then you square root it.
Root means squared.
Yeah.
Squared.
Root means square. You start at the end. You do the square first. Then you do the mean. Then you do the square root. Yeah. So you should know these 4 options. What they, if I ask, find some of the probabilities, you should know.
Those 4 will be on our sheet.
The equations that I wrote won't be on your sheet. That's what you need to know. You need to know these words mean these math.
Okay.
And we're using these things to find that.
You're going to use that to solve. If for anything except for this one here, you're going to have to use that sheet. For this one here, you're doing a derivative. That sheet doesn't. You don't need that sheet to do the derivative, right? You know how to do that.
All right. Well, we'll see how it goes.
And once again, if you just go back to the lecture from the last Tuesday we had class, I did all of these. I would probably go to OneNote and look at the slides rather than listen to the whole thing. But if you are like, ooh, I don't know how he did this, it doesn't make sense on the slide, then you can go find it on the YouTube. All right. So we finished the isochoric case. What we're doing here, Randy, is we're finding the heat, the work, and the change in internal energy for the different thermodynamic processes we've talked about. So we have finished with the isochoric. We had the work for isochoric process is 0. The heat is equal to change in internal energy is equal to the integral of NCV dt, where CV, the molar specific, or the constant volume molar specific heat, is the number of degrees of freedom per molecule over 2 times R. So now we go to isobaric. What does isobaric mean? Constant pressure. So if it's constant pressure, remember work is integral of P dV. If it's constant pressure, you can bring the P out. But what's the integral of dV? V. It's just V final minus V initial. Remember, we always have limits on these things. Right. So that's just equal to pressure times change in volume. V final minus V initial is change in volume. So the work, wow, that was simple. Heat, once again, we define heat as dq is NCP dt. So instead of CV, which was constant volume molar specific heat, now we have CP, constant volume, or constant pressure molar specific heat. But of course, we don't know what CP is yet. That's a definition, but we don't know what CP is. So then we go to the first law. So the first law, du is dq minus dw. Randy, you weren't here when I talked about it. Q is a transfer of energy. It's already a change. And so we have a really weird thing that dq and q are really the same thing. And so that's why we have a different symbol for it. I was taught to put a D with a slash through it, but I was reading before class. I saw on Wikipedia that some people put this D, and I could put this D in my equation editor, and I couldn't put a D with a slash through my equation editor. So that's why I have this D. So that's an improper, if you will, derivative. So the first law using those is du is equal to dq minus dw, which any sane soul says, but it was delta u is equal to q minus w. Delta became d, and nothing became the funny d, the funny delta. So here I've substituted that, and here I've substituted, well, this. And so for a monatomic ideal gas, or excuse me, for any ideal gas, we had the relationship that said, and I've wrote it up here, U is equal to the number of degrees of freedom per molecule times nRT over 2. And by the ideal gas law, you can replace nRT with PV. So for this case, I said, okay, PDV, well, actually, I can just go straight to the ideal gas law. Ideal gas law, PV equals nRT, right? If I take the derivative of both sides, so I take d of this equals d of this, then on the left side, since we're doing the isobaric, P is constant, and the left side is PdV, the right side, nR are constant, nR dt. And so that's what I've done here. I changed PdV to nR dt by using the ideal gas law. Why did I do that? So I have two derivatives, both with the same d, both with the dt. And so that means that I can write my du is equal to n times, if we combine these two, I have an n here and an n here, so I factored it out. I have a dt here and a dt here, so I factored it out. And what was left was Cp minus R. So that's why there's Cp minus R there. But then going back to this equation here, du is f over 2 nr dt. So I replace du with n f over 2 r dt. And once again, David, what is Cp going to be here? What's the first step? Let's do it in two steps so we don't get confused. What is equal to what in this bottom line equation?
Cp minus R is equal to f over 2 times R.
And so if we solve that for Cp,
R times f over 2 plus 1.
Plus 1, yeah. Because I factored out the R. I mean, you were thinking the right thing. So here we have the value for Cp for the constant pressure molar specific heat. If it, well, I say constant pressure, it's already defined. So now we can summarize here that work is equal to P delta V and Q is equal to N Cp delta T, where Cp is equal to F over 2 plus 1 R. And then the change in internal energy is just like before. Delta U is equal to F over 2 nR delta T. So there we have our equations for the work, the heat, and the change in internal energy. We've done the two easy ones now. We did the really easy one, and then we did the one that's a step up. Now it's time to get serious. Notice I just left these as blank pages for the ones that are serious. Isothermal. Isothermal, what does that mean? Constant temperature. Usually what people get confused with is heat versus temperature. Isochoric is constant volume. So isothermal has its own nicety Because for an ideal gas, for any ideal gas, the internal energy is proportional to the temperature.
Right.
The constant proportionality depends on what the degrees of freedom is, but if it's constant temperature, you know there's no change in internal energy. So we know right off the bat for isothermal, I'm just going to write it up here so I don't forget to write it. Delta U equals 0, right? So what are we left to find? Well, from this relationship right here, we have dq is equal to dw is equal to integral of p dv. Oh, wait, is equal to p dv. You have to do the integral sign to get the integral there. Is equal to p dv. So if I want to find q equals work equals integral of p dv, I'll have the last two things we're looking for. But it's isothermal. What does isothermal mean in terms of the ideal gas law? If it's isothermal, what does PV equal to? Okay, it's nRT, and that's constant. Because T is not changing. So what we usually do is we say, well, PV is equal to P initial times V initial. Right? Because it's constant, let's just choose the initials for whatever we have a constant. And so that means in this equation, notice I had integral of P dV. I have to have my function I'm integrating a function of the same variable that I'm integrating over. And so I just say, well, I can rewrite this as P is equal to P0 V0 over V. And so then this integral is not so bad. Integral of P0 V0 dV over V. And we're going to go from V initial to V final. I better put my limits now that I'm getting to actually doing an integral for the first time today. We've done a lot of calculus writing. We haven't had to actually do any calculus. But this is an easy integral. Go ahead, Brandon.
I saw a video just earlier where a guy did that exact same thing. You find what class, but change P to what it was equal to. NRT. No, it was B something NRT. But those were all constants, so we just took it out of the integral, and then natural law somehow.
Well, that's right. That's right. Because we have here P0 and V0 are constant. Integral from V0 to V final of dV over V. What's the integral of dV over V? Natural log. And so that's equal to P0 V0 natural log, putting in our limits V final over V initial. And at this point, I'm assuming you're comfortable with the limit process. Does anyone have a confusion about why I have natural log of V final over V initial?
V final minus V initial, right?
Right. You would have, if you did it long form, there is a mathematical problem in what I wrote. What I wrote is correct calculus. But what's the natural log of 2 liters? You cannot do that. Natural log's argument must have no units. And so I can't just leave it like this because it's mathematical nonsense, even though it's correct.
Right.
But what I can do is when I have one natural log and another one subtracted, that is equal to, and I'll put in green, natural log of the positive one divided by the negative one.
So you can combine them.
Yeah. Now it's not mathematical nonsense because now I have a unitless argument. And of course, people could say, you could do the other one as long as you realize that while each calculation has meaningless units that are going to be a problem, when you subtract them, they're going to disappear. Yeah, I mean, that's correct. But this way here, you have no problem. So that's how we got this. So what was this equal to? That was equal to Q, or the work. So Q equals work equals P0 V0 natural log of V final over V initial. Or you might find it easier to use ideal gas law and say nRT natural log of V final over V initial. If you know one, you're going to be able to do it either way. So there we have, again, change internal energy, heat, and work for the isothermal process. Only one remains. What one remains? Of our 4 processes, we did isochoric, isobaric, isothermal. What's the last one?
Adiabatic.
Adiabatic. And what does adiabatic mean?
Constant. No.
Adiabatic, very literally, it means no flow. Means there's no heat.
Oh.
So adiabatic process, the heat is 0, which means that du is minus dw, or that means minus pdv, right? And once again, if it's an ideal gas, my U is number of degrees of freedom per molecule times nR over 2 T. Or number of degrees of freedom, using the ideal gas law substitute, number of degrees of freedom per molecule divided by 2 PV. So if that's U, then what is du? And we've done this before, but this is where it becomes more interesting. What is du equal to? Okay, F is a constant. F and R are all constants.
Where is it hard? What am I thinking?
Since F is a constant, FO2 stays unchanged. N is a constant, stays unchanged. R is constant, stays unchanged, and I just have dt, right?
dt, a change in temperature.
Yeah.
But there should be a change. There's no heat. Right?
Yeah, no heat does not mean no change in temperature, because I can have something that's insulated so no heat moves in or out, but I can compress it. For instance, consider a bicycle pump. You have a bicycle pump. If you plug the end so no air can get out, you push down on it. If you do it really quickly, you don't have time for heat to flow. What happens to the temperature of your bicycle pump when you do that? It gets hot, yeah. And so when you pump up a tire, yeah, you didn't stop it, but you're still compressing very quickly, and so the temperature goes up, and you can feel that pump get hot. So you're going to have a change in temperature even though there's no heat, because you put energy in. Or using the second half, this could also be F over 2 D of PV. If I'm taking the derivative and I have two things, what do I have to use? Product rule. So that's equal to F over 2 P dV plus V dP. There's product rule. And at this point, it probably does not look clear that I'm going anywhere. Is that correct? Dave's all, yep, it looks like you're not going anywhere. Okay, so what am I trying to do? I'm trying to find equations for what I'm going to have for my work, change internal energy, and heat. What's the heat? 0. That one's done. So I'm going to take this equation, du equals, from the first line, that was equal to minus PdV. From the second line, that's equal to, and I have two forms, one that's in terms of dt and one that's in terms of PdV and VdP. Which one of those seems like a logical one to use? Logic may fail you.
Just the NRDT.
Okay, and that's where logic fails you, but I can totally see the logic because it's simpler, right? But we actually used the second one, the one with P and V, because we had two variables. Come on, slide. We had two variables there, P and V. And so we used the form over here that had the two variables V and P as well. Right, so instead of choosing the one that's simpler, We choose the one that has the same variables. So this is equal to F over 2 P dV. Oh, I forgot. There's a minus sign. No, there's not a minus sign. The minus sign's there. Plus F over 2 V dP. Now we're down to the kind of math we did first day of the semester. I have a differential equation with two variables. How can I solve it? Separation of variables. What he said, which has the name that you said. So you guys got that. Nailed it. We should take the test as a team and you guys have this covered, right?
I like this plan.
I got the words. I've got the method. We're good. All right, so separating variables. First thing I'm going to do is recognize this is PdV, this is PdV. I'm going to move this to that side of the equation. So I'm going to have a minus parenthesis. This one here was 1 out front. This one here is F over 2. So 1 plus F over 2 PdV. That's the left side. Right side then has F over 2 V dP. Haven't separated any variables yet. I just separated so I have dP on one side and dV on the other. What should I do next? I need to separate the variables, so what do I do next?
So you do substitutions where you equals one thing and
I divide. What do I need to divide from the left side? I'm going to do that actually. I'm going to divide F over 2 from both sides. That's not necessary at this point, but I'm going to do it at this point.
you divide dV by the from both sides, don't you?
Not dV. The d's have to stay in numerator positions.
Okay. Then it's P.
I have to divide P so that this P will disappear. What about on this side? What do I have to divide by? V. So that will disappear. So now I'm going to have my V's cancel there, my P's cancel there, and my F over 2's cancel here. And so what I'm left with is dP over P. So I reverse the signs on the equal sides of the equal sign.
Aren't you supposed to divide B on the other side as well?
Yeah, divide B on the other side.
Thank you. Yes. Because that's kind of important. Let's see. Equals minus F over 2 plus 1 over F over 2 dV over V. Now, before I go forward, we make a substitution to make it shorter to write. We've gone through and we found what CP is, and we've gone through and we found what CV is. So recall from our previous work that CP was equal to F over 2 plus 1 R, and CV was equal to F over 2 R. And so if we take those, we divide them.
Why don't you cancel out the F over 2's on the one side?
I did.
No, on the other side that we divided.
Well, it's 1 plus F over 2 divided by F over 2. So if you look at the CP over CV, what's going to cancel there? Looking at this right here.
The R's.
The R's cancel.
So then you're going to be left with 1 over F over 2.
Not so simple. It would be 1 plus 2 over F would be what it would be. Right? Because F over 2 divided by F2. But we just defined that as gamma. And so that's what we had right there. And so this is just minus gamma dV over V. What's the point of gamma? The point of gamma is to just save us writing. That's the whole point of it. So now I have a differential equation. I can integrate it because I separated the variables. So I'm going to integrate this one from P initial to P final. And this one, from V initial to V final. What's the integral of dP over P?
Natural log of V.
Natural log of P.
Oh, sorry, wrong side.
And what's the integral of dV over V?
Natural log of V.
So there, I wrote them in a different form just to give you some remembering, showing the limits, or applying the limits as we did before. Natural log of P final, that's P final, over P initial equals minus gamma natural log of V final over V initial. At this point, calculus is done, but the math is not. What am I trying to solve for? You probably have lost track of that.
Yes.
What I'm trying to solve for is to find the change in internal energy, which is equal to the work in an adiabatic process. What I have here has no work and no change in internal energy. And so you're like, I think you took a wrong turn somewhere. I didn't.
I'm assuming not.
Because what I'm going to get here is a relationship between pressure and volume that then I can go back to the definition of work and integrate to find what the work is. So what I'm going to look for in this step is the relationship between pressure and volume, and then go back to integrating the work. So if I want to find the relationship between pressure and volume, this is a relationship, but it's not pretty. How can I make it pretty? Translation, how can I make it usable for me?
Raise it to E or something.
That's right, but there's a step first. Because I have this minus gamma out here, if I just do the raise to E, it's going to be a little clumsy looking. We can still do it, but it's just going to be a little clumsy looking, take a little more work. But I can rewrite this as natural log of V final over V initial raised to the minus gamma. You take that thing that was out front and you just raise the argument. But of course, that's a negative exponent. So it reverses, so I can write that as natural log of V initial over V final raised to the positive gamma. Now I can do what Randy said. Now we'll do the exponential because that's the inverse function of natural log. So if I do the exponential, which 2 to 1 you have to do to each term in the whole line. Can't forget any of them or else you did bad math. I only care about the first and the last. There's equal signs all the way through. And so what I have for the first one is E raised to the natural log of P final over P initial is, you guys are all over this. And for the last one, E raised to the natural log of V initial over V final to the gamma is, so we usually just go ahead and rearrange this to say P final, V final to the gamma is equal to P initial, V initial to the gamma. Erase the F's because it's true for any case. And now we have P that we can solve just like we did before as a function of the volume. So if I want to get this P as a function of volume, I have P is equal to P initial, V initial to the gamma, divided by V to the gamma. Got 3 minutes left. We can do this. We now have a relationship between P and volume, pressure and volume. Going back to my purpose. What's my purpose? Find work. And to find work, I need to integrate P dV. Work equals the integral of P dV from V initial to V final, right? And so using that equation, that's the integral from V initial to V final, P initial, V initial to the gamma, dV over V to the gamma. Take the constants out. Integral of dV over V to the gamma.
Natural log of V to the gamma.
Only if gamma was 1.
Oh, wait, it's
How about we write it this way?
V negative gamma plus 1 over negative gamma plus 1.
So it's going to be, you raise the power by 1, divide by the new power. I'm going to change it to 1 minus gamma because that just looks nicer. Although it turns out that's a negative number I divided by now. So now let's put in our values, our limits, I mean. So that's P initial, V initial to the gamma, all over 1 minus gamma, times V final to the 1 minus gamma, minus V initial to the 1 minus gamma. And when you look at that, you start to be a little annoyed. I do, at least. And so I'm going to spread it out even more. It seems like it should be more annoying when you spread it out, doesn't it? So I have P initial, V initial to the gamma. I'm going to put out front 1 over 1 minus gamma. P initial, V initial to the gamma. V final to the 1 minus gamma. Minus P initial, V initial to the gamma, V initial to the 1 minus gamma. The second term in this is kind of simple. What do I get when I multiply these two together?
We can multiply up to add the exponents.
That's right. So what's gamma plus 1 minus gamma? 1. Woo! How nice is that? Now, this first term, remember, we had the relationship that P final, V final to the gamma is P initial, V initial to the gamma. So I can take this right here, and I can change those initials to finals, and it's still true. It's equal to the same thing because that was my constraint for pressure and volume if it's adiabatic. And so then if I do this initial one, that's going to be, following Randy's work, P final, V final minus P initial, V initial. And so in the end, work is equal to P final, V final minus P initial, V initial, all over 1 minus gamma. Or if you prefer using the ideal gas law, equals NR T final minus T initial over 1 minus gamma.
Those guys out there derive all this together.
What was that?
The guys in the other class. They don't.
No. No, they do not. I just gave them these equations. Now, this won't be on this test, but this is material that could be tested on the final exam.
Sure.
So what we have done in the nice job now is found the equations that allow you to calculate pretty much what's going on in any thermodynamic process, that as long as it's one of the four that we've talked about: adiabatic, isothermal, isochloric, or isobaric.
This all won't be on the test. It's like chapter 16.
These derivations will not be on the
I
test.
see, but I think they're on.
The equations that we came up with, the end equations, yes, those are on the test. But here you can see where they come from. It's not matching. Right? Even the equation that PV to the gamma is constant, I used it in class yesterday to explain how to do that last homework problem. Without calculus, you have no basis to believe that's true except when the teacher said it's true. But now you've seen, it wasn't straightforward, but I can see how we get there. So for the final exam, I could ask you to show why for an adiabatic process, PV to the gamma is constant. Or I could ask you to show, given that for an adiabatic process, PV to the gamma is constant, what is the work? I would not ask you to start from the beginning and do both pieces, just because the time would take. Any questions?
This class is kind of more for understanding why things are the way they are.
Yeah, because that's where calculus is beneficial, I think, in physics. And well, when we get to next semester, there's just problems you cannot do without calculus. I can't even introduce them in general physics because you really have to do calculus to do anything. And so next semester, there's just problems that they can't do.
Calculus isn't that bad.
Why do you do that?
I think people.
Yeah, calculus itself isn't too hard. Well, looking at all of this and getting all these equations, it's like.
And that's what theoretical physics is all about.
Yeah.
Physics, you can have theoretical physics, you can have experimental physics, that's what I am. You can have computational physics, which is where you solve physics problems using computers.
Why don't we do experimental physics?
Because those are all professional areas, they're not introduction. Because all of them have to understand the stuff working.
Yeah. The theoretical stuff.
I have great respect for theoreticians because I'll tell you, that is hard.
No doubt.
What do they do?
They do this kind of stuff at all levels, right? We're doing the beginning stuff, which seems hard, right? I mean, it is hard, but they're doing much harder problems.